I was asked some time ago to be a moderator of this fourth webinar that is jointly organized by the STAD project and the Meaningful Human Control project. The STAD project is a 4-year joint research project about the implications of the future of accessibility and spatial development of mobility with respect to autonomous driving technologies. And the Meaningful Human Control project focuses on socially responsible transition to automated vehicles and develops guidelines for this. And central in this project is the development of a theory called Meaningful Human Control. There were 3 webinars before this, and you can find their recordings and presentations online. Before I introduce myself, there are a few household rules. We ask you all to switch off your microphone and video. You can ask questions. We would like to ask you to do that via the chat function. We will try to answer all the questions either right after some of the presentations or at the last part of the session. The URL is now seen on screen. You can find all previous and the upcoming presentations there. And this session is also being recorded. The agenda for today is that first I will give an introduction and a European Commission perspective on connected and cooperative automated mobility. Then Anirudh will give a presentation on the spatial and temporal synchronization of truck platoons, and Simeon Calvert gives a presentation on what does vehicle automation with meaningful human control mean in practice. And then at the end, we have some time for questions and debate. So for those of you that don't know me, my name is Tom Alkim. I worked for about 20 years at Rijkswaterstaat, so I can also speak Dutch, but we do this session in English. You can see me on the top left. I'm also in some of the other pictures. I selected some from around the world. I am currently in Brussels, working for DG Research and Innovation, and in that capacity we organized the Connected and Automated Driving Conference last year with a small team. You see my colleagues Susanna Kraakman and Ludger Rogge on the right. And you also see a picture here with the To Get There vehicle taken last year at ITS Europe in Eindhoven, one of the L3 pilot vehicles. That's one of the European projects. And I've also been to several truck platooning demonstrations, and I was also involved in the European Truck Platooning Challenge already 4 years ago in 2016. So as a starter for this session, as I told you, I work for DG Research and Innovation, and we are responsible for the research budget for European projects in Europe. And I would like to give you a little overview on what we expect of that. A few words on hyperreality, on the operational design domain framework and how we relate a lot of projects to the challenges it raises. A few words on the CCAM partnership in the future. And finally, some ethical aspects of connected and automated driving, since I think it links quite nicely with the second presentation. So at the European Commission, we have a comprehensive approach to support the development and deployment of connected and automated vehicles in Europe, where we think we need to develop an app legal framework, take into consideration societal and ethical aspects, and the investment in research and innovation is an important element. We do this because we think that, and the term that we use is CCAM, connected, cooperative and automated mobility, has the potential to make transport safer, greener and more accessible. However, there are several challenges that need to be addressed, and they go beyond the key technologies, although it's a very important aspect. The right legal framework has to be set up and adopted at member state and EU level. Also, connected and automated vehicles will need to be integrated into the broader transport system and interact with other forms of mobility. So in other words, we don't think a connected and automated vehicle is a silver bullet to solve all your mobility problems. And finally, acceptance and trust in this CCAM technology by users and society has to be nurtured every step of the way. Without this, you can have technology that works and a legal framework that allows it, but if you have people that don't want to use it, you will not get the benefits. As you may know, we are currently in the Horizon 2020 framework. It's a 7-year framework, and we funded a lot of calls. The budget is approximately 300 million euro, and we are now at the final stage. We had to focus on quite a lot of different elements of CCAM. I put in red the large-scale demos of automated driving systems for passenger cars, trucks, and urban transport, as I think they are quite relevant to this webinar, and especially Ensemble, since it is about multi-brand platooning. You can find all the information about the ongoing Ensemble project at the URL that I put below the symbol. But as you can see, a lot of other aspects are also being funded at different projects. Two of the latest projects that have just started are SHOW and HADRIAN. SHOW is about developing and testing shared, connected, and cooperative automated vehicle fleets in urban areas. So in a sense, that's also quite relevant to the STAD project. You can see a bit of information here. I think it's a quite large consortium with 69 partners, and international cooperation is foreseen. You can find all the information on this project at this URL, and it will last for the next 4 years. The other project, HADRIAN, also just started. It is about the human-centered design for the new driver role in highly automated vehicles. And it will focus on the design and how to incorporate the role of the human in the, let's say, in the teamwork between machinery and humans. You can find all the information on this project on this URL. And then I would also like to announce that the final 2 automated road transport projects in this framework are currently in the granting process. Sorry that I cannot announce them today, but one of them, ARTO 5, is on efficient and safe connected and automated heavy commercial vehicles and real logistic operations, and that includes truck platooning as well. So that's quite relevant for this webinar. A few words on hype and reality. If you look at all the Gartner hype cycles over the past 10 years, this was the first one that I could find where autonomous vehicles appears. You can see that in 2010, it was expected that it would take more than 10 years to develop. Well, we all know that it's we are 10 years later, but it has not happened. If you look at all the different cycles, in 2015 you saw that it was at the top, and at 2017 Gartner made the choice to make a distinction between at least level 5 and level 4 and put them on different spots on the Gartner hype cycle. The new one will appear any minute now, probably next month, so we can take a look at where it is. But I think The overall message I would like to give here is that we are not in the phase of inflated expectations anymore. If you went to conferences in 2015 and 2016, there were a lot of really nice stories how in a couple of years the whole world would change. Now we see that it is a bit more complicated when you apply theory and practice. And I think that is also something that we will learn today. Then a few words on the operational design domain framework. This is something that I did in my time with Rijkswaterstaat, where we try to envision the operational design domain. This is the area or the set of conditions under which automation is functioning. And in theory, you can depict it like this, but in practice, it's a bit more complicated because due to a lot of external factors that not always can be controlled, the operational design domain will have some gaps. This is usually because of infrastructural shortcomings or complications. It can be other traffic. It can also be adverse weather conditions. And I think that one of the joint tasks that we have with industry, policymakers, academia, is to try and optimize the area of the operational design domain. In practice, or what we try to do at the Commission also is to position a lot of the projects so that they can deal with several of those challenges. And as you can see here, there were a number of projects looking at the relationship between automated driving and infrastructure, such as Coexist and Transaid, Inframix, and Maven. And here you can see that quite a lot of projects are related to one of the reasons for gaps appearing in the operational design domain. Of course, trying to control the weather is a bit more complicated. That is something we will have to deal with for a long time. And on the left, I put several large-scale demonstrations. L3 Pilot is basically dealing with person vehicles, Ensemble with freight vehicles, and Show with public transport solutions. We think that it's really important to try and find solutions based on actual practice. When you take your concepts to the roads, that's where you will see the complications, and you need to go back to the drawing board and try to improve and improve. So we think that this iterative process really is valuable. A few words on the CCAM Partnership. This is a proposed upcoming public-private partnership to better align European research and innovation efforts in the upcoming Horizon Europe framework. That's the next 7-year framework, in which we will fund, again, a lot of projects related to connected and automated driving. And, well, this is, of course, to improve safety and security of road transport, meet societal and market needs, including the inclusiveness and accessibility of mobility and more efficient traffic flows. Of course, we try, and in light of the Green Deal, we try to look at reducing environmental impacts, including congestion, air quality, energy consumption, and climate change, and also try to increase the effectiveness of R&I by doing this in this public-private partnership. This will be a multi-stakeholder partnership. You can see the different stakeholders that are currently involved. There is still room for more stakeholders to join. And what I just wanted to show here is the 7 clusters that are currently in the partnership. As you see at the center, we have the large-scale demonstrations at the heart of it. We expect that most of the funding will go in that direction. And as I mentioned before, this is really important because in practice is where you can see if it works the way you intended it to work. And around that, there are different clusters dealing with in-vehicle technology, validation, integrating the vehicle in the transport system, key enabling technologies, social aspects and user acceptance, and also research coordination. I put these 2 clusters in red because I think they have a relation to the topics of the webinar of today. So automated commercial freight vehicles, their truck platooning plays a role, and the human meaningful control has a link with the societal needs analysis. I'm getting to the final slides of my introduction, the ethical aspects of connected and automated driving. This is an aspect that we think is quite important. It has been raised over the past few years, mostly in the media in the form of a classic trolley dilemma, which is nice for a lot of discussions, but it's very difficult to have practical solutions for that. So that's why in June last year, we formed an independent expert group to tackle specific ethical issues that go beyond these dilemmas. We had 14 different experts from the fields of ethics, law, philosophy, and connected and automated mobility from all over Europe. And they wrote a report with 20 recommendations. It is finalized. It is not publicly available yet. It will be published any moment now. We are just waiting for a moment with the commissioner to promote this report, but it will become available soon. The vision is that technological process alone is not sufficient. So from inception to use, the timely and systematic integration of ethical and societal considerations will be essential. And in the second presentation, the third presentation today, you will hear a bit more about that, and also how difficult it is to operationalize these concepts. In this report, also concepts from the Human Meaningful Control project are being used. Maybe interesting for you to know is that the Filippo Santoni, the CEO, who is in the Human Meaningful Control project, was the rapporteur for the expert group. The 20 recommendations in the report are centered around 3 key themes. The road safety, risk, and dilemmas is one. The other one is data and algorithm ethics, privacy, fairness, and explainability are related to that. And finally, responsibility. So the publication will be next month. For each hub, there are different actionable next steps formulated for different stakeholders, for policymakers, researchers, CAF manufacturers, and deployers. And we will agree on an action plan to translate all these recommendations into practice soon. So thank you for your time. Let's see, time-wise, we may have time for 1 or 2 questions. I don't see a lot of questions. There is one. No, we'll skip that one. We'll go to a little poll. That's maybe nice to do now. I have to click a few buttons to make this work. But I was wondering what your opinion is on when will we see operational cross-border multi-brand truck platooning in Europe in practice. A is before 2025, B is within the 5 years after that, C is after 2030, and the final option would be never. So I see that you have started to make up your mind and click some buttons. Let's see how many participants we have and how many of you have voted. About 70% of you have voted, so I will wait a couple of minutes before I will publish these results. I see that we have a lot of smart people in the audience, meaning that we are neither too optimistic or too negative. So most of the options are around B and C. I will publish them right here. Yeah, we may be quite optimistic because cross-border multi-brand platooning is not easy, but it would be good if we can see it within the next 5 to 10 years. Let's see. There's only one way to find out, and that's in practice. Okay, now we go on with the program. I will introduce the other two speakers briefly. The first speaker is Anirudth Kishore Bhoopalam, and he is a PhD candidate at the Rotterdam School of Management. His research interests lie in the application of operations research methods and quantitative models to transportation systems. He currently does this as part of his PhD in the context of truck platooning. And he began his PhD just after finishing his master's in transport, infrastructure, and logistics at the TU Delft, where he became particularly interested in automated driving. His presentation will be on spatial and temporal synchronization of truck platoons, and some of the items he will explain are what kind of considerations do we need to make while planning platoons, how can we maximize platooning benefits, and can it be done in a simple yet powerful way, and how do truck drivers think platooning will affect them. The next speaker is Simeon Calvert. And Simeon Calvert is an assistant professor in traffic and network management at Delft University of Technology. His main expertise lies in traffic flow modeling, traffic management, and impacts of automated driving and technology on traffic flow. He previously worked at the Research Institute TNO and has a broad experience in numerous European and national research projects. He also co-leads the Traffic Data Analytics and Simulation Lab in Delft, the DIT Lab, and the Delft AI Lab on urban traffic and mobility behavior with AI, the City AI Lab. So his presentation will be on what does vehicle automation with meaningful human control mean in practice. And he will consider the importance of operationalization of the concept in practice. He will talk about how they applied this to the case of truck platooning for evaluation and demonstrate an operational example of meaningful human control for automated vehicles and infrastructure design. Looking forward to hear a bit more about that. And then there will be one more webinar on the 10th of September in which Pablo, Daniel, and Rian will present on behavior, so the behavioral aspects of automated driving. And this session will be moderated by Peter van der Knaap from the SWOF. Okay, I guess at this moment I hand over to the next presenter, and thank you for your attention so far. We will take questions after Anirudh's presentation. Thanks.
Hello, good afternoon. Yeah, so this works. The webcam took me a while. But yeah, thank you, Tom, for the introduction. And I'm going to be talking to you all about spatial and temporal synchronization of truck platoons. This is work that I largely did as part of my PhD with my supervisors, Sadvak and Niels Alchatz. And my presentation is divided into 3 parts. I'm just going to give you a background of what platoon planning is and some of the things you need to consider while needing to plan platoons. Then talk about the spatial and temporal synchronization, some methods we came up with and how they perform. And finally, a final behavioral study we did where we spoke to truck drivers to see what they think about platooning technology. So for each of these points on the presentation, I will start off with a main message and then tell you some more about it. I think I need to click, yeah. So platoon planning background. So first, I'd like to say a little bit about why we need to plan platoons. So platoons, the main benefit is the saving of fuel. So the fuel cost goes down. And experiments show that the fuel cost goes down by about 2 to 15%, depending on the conditions and the study you look at. So in perfect conditions, it's higher, and in real life conditions, it tends to be a little to the lower side of that interval. So the benefits relatively are not that high. So it's pretty important that they plan well so that we can reap as many benefits as we can. Furthermore, platooning is likely to be the first implementation of automated driving out in the open. So it sets a benchmark. So it's quite important that it works pretty well to gain public confidence and everything that comes with it. Yeah, so the main message from this background and literature review and everything that we did is that, there's still some way to go. As in, there's already been a lot that's accomplished. Most people look at different parts, but the sum of them hasn't been looked at yet, and I will talk about it further. So first, I'd like to just explain what platoon planning entails. So this is a very simple picture of a platoon where we have origins, destinations of 2 trucks, and we know the origin, and we also know the time schedules. So an earliest departure and a latest arrival or a deadline. So we need methods to determine routes of these trucks with platooning. So where they meet, where they split up, if they need to wait at some point with another truck to be able to form a platoon with another truck, or make a detour, for example, to be able to form a platoon with another truck. So you also decide everything about the time when they meet, how late they meet, and so on. So this is just an example with 2 trucks. Obviously, it can get more complicated with more trucks coming and leaving and so on. Some things we need to consider while planning these platoons is the degree of centralization, the level of automation, and the dynamics. I will talk a little more about the degree of centralization and the level of automation, because dynamics is fairly standard. You have real time and something that's done before. So you do it when the trucks are driving or before. So there's not much room there, but with the degree of centralization and level of automation, there's quite some differences in how they affect the planning problem. So the degree of centralization, it's, I think, a spectrum, but you can see the 2 ends of it. One is where you have a platoon service provider, basically a computer planning routes of many trucks, which is indicated by this. Or on the other side, you have, which is completely on the fly or ad hoc platooning, as they call it, where a truck is driving on the street and then it sees another truck and asks if it wants to platoon, and if yes, they do. If not, they're on their way. On-the-fly platooning sounds very appealing and is by far the easiest because you don't need any planning infrastructure or any effort or computation power. But especially at the beginning, when not a lot of trucks have platooning technology, it's quite likely that this won't work because a truck on its route will never find a platoon. Therefore, at the beginning, it's quite likely that we use a centralized approach. In addition, there have been quite a few studies that show that a centralized approach is far more beneficial than an ad hoc approach, even when a lot of trucks have platooning capabilities. So that's what we do a little later, which I will talk about. And the levels of automation also influence the nature of the planning problem. So the first step in platooning is human-driven platooning. So you have drivers in all the trucks that are attentive at all times. They get assistance from the system, of course, but they have to, for example, be ready to leave the platoon and join in and still do some steering and so on. And the planning for this is basically the exact planning problem that I discussed. The next form of platooning is human-driven platooning with in-platoon resting. So in theory, the drivers in the following trucks can take breaks. So they don't have to physically stop according to regulations, while taking breaks. And there must be obviously some physical breaks where they have to stop. So trucks in theory can drive longer. This really influences the planning problem because you have to take these regulations into account, and these regulations differ from country to country, continent to continent. So the problem would change in nature quite a bit depending on whether you're doing it, for example, in the EU or the US. You already see this with normal truck driver scheduling, different problems for different regions, and that will become even more complicated when you take platooning into account. And the next step would be, okay, this should say hybrid platooning, so I think the heading is messed up. But yeah, you have a driver in the lead truck of a platoon and no drivers in the following trucks. However, when a truck leaves the platoon, you still need a driver. So the biggest planning issue now is how would you get that driver into the truck when the truck leaves the platoon? Would you, for example, have these some sort of shuttles or taxis that are driving around transporting drivers between the split points and meeting points of platoons? And that itself is a planning problem. How do you plan these trips? Or do you have some sort of physical hubs where drivers wait? So yeah, there's a lot to be considered here. And it's the first big, proper fundamental change in the way things work. Yeah, I switched the heading, sorry about that. So this should be fully automatic platooning where no drivers in any of the trucks. And planning-wise, this is actually not that difficult because if you think about it, it's the same as the first form of platooning where drivers are in all trucks, so you don't have to think about driver breaks or anything else. It might be even more flexible because with drivers, you need trucks to return to depots so that they can go back home at least once in a while, depending on how their contracts are. But here you can have it really flexible, so trucks don't have to come back, so they can just stay somewhere, and then it opens up a lot more of a collaboration. So I'll talk about a couple of conclusions that we had from this part of the research. I will show the whole thing already. So there's still a lot of room to work in when it comes to optimization. A lot of sophisticated meta-heuristics still haven't been applied to platoons. Also, a lot of researchers consider the first form of platooning, and recently a study came out with break times included. But for the more automated platoons that I just talked about, there's pretty much no research out there. Also, all these planning methods don't really take uncertainty into account, like stochastic planning and the effects of congestion. There are, of course, studies that do this at a micro level. So, for example, they look at how it affects congestion on a stretch of a highway, for example, but not really on how this would affect the whole system and how it would affect the entire system of trucks along the entire route. System sustainability is also really important here because, especially with multi-brand platooning, you need different companies to collaborate. So there's quite likely to be strategic behavior if it's not designed properly. So you need to design a system in a way that there's no incentive for anyone to lie about their preferences. By lie, I mean you can have some companies say that my truck is driving to somewhere else just to be able to get a better match in terms of platoon. So a system needs to be designed in a way that they have no incentive to do this. And finally, network design. Should the infrastructure be developed to, facilitate these platoons, like separate platooning lanes or platooning hubs along big cities and so on. So the main conclusion from this part of the PhD was that there's still a lot that people need to take into account while planning these platoons. Now I will talk a little bit about what we did in terms of trying to help contribute to the literature and come up with methods to plan platoons. And the main message from this study we found that was simple two-truck platoons capture a large chunk of the benefits that you would get if you use much more complicated platooning arrangements. Yeah, I will explain further. So for this study, we considered this setting. The goal was to minimize costs, and we considered centralized human-driven platoon planning. So we planned it from we're like a platoon service provider. We assume that all trucks travel at the same speed, and we know all information before this planning process begins. So yeah, it's static. So there are two problems that we look at here: the truck platooning problem and the truck pair routing problem. So the truck platooning problem is, we can come up with configurations like these, where you allow multiple trucks per platoon, and each truck can be part of multiple platoons per trip. So for example, in this arrangement, we have 4 different platoons depending on when trucks arrive and leave. So it can be far more complicated with more trucks coming in and more trucks leaving. But on the other hand, the truck pair routing problem is much simpler, where you just have 2 trucks, and they can only be part of 1 platoon per trip. So you meet a truck, you split up with that truck, and you drive on to your destination. Yeah. And how do we solve this? So for the big truck platooning problem, we come up with a 2-phased mixed integer program based on a time expanded network, and we can restrict the number of trucks in a single platoon. So for example, each of this, we can say that each platoon can have only 3 trucks at max. So for the next one to join, one would have to leave earlier. So we can make those kind of restrictions. And the truck pair routing problem, we reduce it to the shortest path problem, which is very easy to solve. Has been studied for tens of years now. And then we can do that for all the pairs of trucks we have in the system, and that find the optimal matching to be able to find a platoon partner for every truck in the system. Yes, so we wanted to check how well these simple 2-truck platoons perform. So we come up with heuristics for the big truck platooning problem based on the approaches we have for the truck pair routing problem. So we do this by testing it on a network that represents the Netherlands, of at least the highways in the Netherlands. And we assume that the fuel savings factor is 10%, which can be changed pretty easily since it's just a parameter. And each truck has a flexibility of 30 minutes. So this 30 minutes is basically means that they have 30 minutes to wait along their trip, or potentially take a longer route to be able to form a platoon with another truck. And they can still make their deadline. If they have to do something longer, then they wouldn't form a platoon, and that would be infeasible. So before I show you exactly how this compares to the truck platooning problem, just have a quick poll. So what do you think the percentage cost is? A difference in cost is between when we optimally plan it this way compared to asking all trucks to take these simple platoons, and using these heuristics. What is the percentage gap? How much worse is B when compared to A? I can add that. I can still see responses coming in. So and I think I will leave it on for a few more seconds, maybe 10, 15. I think I will publish the results. So yeah, most people think it's between 10 and 20%, something greater than 20. Yeah, I think, C is a clear winner, but otherwise it's a fairly even split. Well, at least for this study, the majority is not correct. So C wasn't really what we found, as you will see. So how well do these heuristics perform? So the answer was A, actually, and by quite a distance, because we see that we have 3 different heuristics, all based on the same procedure, same ideology. And we see that 2 of them get to within 1% of the optimal solution, depending on the number of trucks. So there should be a 10 and 50 here. So yeah, not sure why that is. And the worst performing one, which is what we call the Euclidean heuristic, gets to within 2 to 4%. So it seems to appear that as all these simple 2-truck platoons capture a lot of the benefits that these more complicated platooning arrangements have to offer. But what's the benefit of using these? We can see that they're much quicker. So how quick are they? So yeah, this is a big table, but I'd like you to mostly direct your attention to this. So all these times are in seconds. And we can see that for example, with 50 trucks, you can find this solution get really close to the optimal solution in about 4 seconds. And to actually find that optimal solution with 3 trucks allowed in a single platoon would take you 873 plus 189. So that's almost 3,000, 2,000 something seconds. So this is considerably quicker, and therefore saves a lot of time and computation effort. Furthermore, when you have more trucks in the system, finding the optimal solution would take longer. Obviously, the times don't scale up. It would just take a lot longer, and these heuristics can provide you an alternative to find near optimal solutions in much, much shorter times. So one we can see here is that simple 2-truck platoon arrangements with 1 platoon per trip provide a lot of the benefits of more complicated platoons arrangements. And simple 2-truck platoons are more easier to coordinate and more robust in practice. So what I mean with this is that you can, for example, make changes much more easily, because if there's a change in the plan of 1 truck, only 1 other truck is affected, its platoon partner. But on the other hand, in the other situation, if there's a change in the plan of 1 truck, then potentially multiple trucks can be affected, and it just propagates throughout the system. So it's much more robust in that way. So some other key takeaways from the study. The first was that they perform well and provide practically robust solutions. We also have an improvement procedure that I didn't show the results of, but they even reduced the gap even further in just a matter of seconds. And one more interesting finding that we had was that a lot of trucks form platoons with an adjustment in their time schedule. They really don't want to make detours because detours cost a lot in terms of extra fuel, which eat into the platoon savings. So average detours are under 1 kilometer. So by even potentially looking at it like a scheduling problem, you can save a lot of computation power and get a lot of the benefits out of it. Finally, this is the least developed part of the PhD for now, so I will do this a little quicker. So extract possibly existing different driver views on platooning and how they think it will affect their jobs. So the main message, drivers are not very enthusiastic, which I don't think is very surprising. So I'll talk a little bit about the method because I found it quite interesting, especially the data collection process quite interesting. So we wanted to do focus groups for which we visited different truck stops in the country. So where truck drivers stop at night. So it's basically something like going to these restaurants and asking drivers if they want to participate. And if they do, we just sit around the table and chat over a drink, basically, with obviously structured questions and get their feedback on how it's going and record everything with permission and then analyze the data that we receive. We structured this according to the different forms of platooning we had. So we asked them the same questions for each form of platooning. And we had a focus group of between 4 and 7 people that lasted each session an hour, but some of them lasted even longer. The language was in Dutch, which, so I was the moderator, was a colleague, and getting truck drivers to participate was a challenge, which again is understandable because we were people that showed up at 7 o'clock after a long day asking them to answer questions. And I think they didn't really, some of them didn't really appreciate that. But ultimately we got what we wanted, I guess. So some quotes that we had during this focus group study was that truck driving is like a paid hobby. So a lot of them are really passionate about what they do. One even went as extreme as saying that if platooning became a reality, they will quit their job. And yeah, some of them think it can become a reality within 5 years. Some people think it's 20. And this last quote was said by multiple people in different forms, that everyone needs to have this technology for us to see its benefits. Yeah, that makes sense even in terms of planning. So the overarching results from this part of the study was that drivers really differ in their views on what they think about technology. It's a lot of preference. So some people think any kinds of technology will make their job easier and safer, but they do take away autonomy. So an example was that a few decades ago, everything was on paper, but now the employer knows everything about where they are, what they're doing, how long they've stopped, and so on. So it takes away autonomy. Yeah, so they're not very enthusiastic about it, mostly because the loss of autonomy, especially when we asked them how they feel about having brakes in the truck, and yeah, they didn't really seem to appreciate that kind of thing. And they think that the job might become obsolete, and this is like a stepping stone towards full automation. And as much as we tried to get them to not think about the doubts and capabilities of the system, as in we tried to assure them that the system will be fine, what would you think it will affect you? They all seem to express doubts. They're always worried about safety and traffic situations, and they seem to worry that experiments are not enough to be able to actually implement this in real life. So yeah, this was a very interesting process of data collection and talking to these drivers. So that was my conclusion of part 3, and that was my presentation. And if anyone has any questions, I will be happy to answer them later, I think. So yeah, thank you.
Okay, thank you, Anirudh. We do have a question from the chat box. So Francis Ostermeyer asks, are these cost differences small because the benefits from fuel reductions are small? And what happens when you change the cost saving parameter? Can you provide an answer to that question?
Yes, I can. So the cost differences, I'm not sure if they're exactly small because the benefits are small. But yeah, I definitely think that plays a role. And sorry. Yeah, my webcam is back. But yeah, we're actually testing what happens when the fuel reduction parameter increases. So I would expect it to go, the gap to become a little larger, but then not much larger because these are quite small. So absolute terms, it shouldn't go above a few percent.
Okay, then I also had a question. You showed this picture of the let's say a solution for the Netherlands where you did some modeling, and one of the results was that there was a 10% fuel reduction.
Yes. Yeah.
With 30 minutes flexibility for all the trucks. So I have two questions related to that. And has this been, let's say, calibrated with practice? And the other one is, to what extent are you taking into account actual platooning conditions? Are you assuming that the trucks can platoon 100% of the time of their trips? Because in practice, you quite often see that due to other traffic or other conditions, you cannot platoon all the time.
Yes. So to answer your first question, it has not been completely calibrated with practice, because we asked some practitioners at the beginning of the study how long they'd, for example, be willing to wait. And some answers we got with that, they wouldn't be willing to wait even 1 minute, for example, or have an extra 1 minute. Mm-hmm. So that's something like a parameter that we're just playing with. So it's just a parameter in the model, and we just took 30 minutes because it seemed proportionately suitable for the size of the network. The network itself has been calibrated, so all the distances are from real life. And your second question, we don't really consider traffic into account because it would just make the problem a lot harder to solve. It's already quite complicated to solve and doesn't scale up, so we don't really consider traffic. So in theory, yes, they can platoon from their origins to the destination for the entirety of their trip, but yeah, there's nothing about the traffic in there.
Okay, so that would be an interesting next step from some video footage that we had in the past. We observed approximately 50% of the time of platooning. So you could try that as an example if you assume that you can only platoon for 50% of the time. Would be interesting to see what the results would be.
Yes,
I have two more questions. I think we can take them before we go to the next presentation. So there's one presentation on how did you introduce truck platooning to the drivers when you interviewed them?
Yes, so we introduced it as this technology, like we specified what the technology exactly was. And since our goal was to see what they think about how it will affect their jobs, we told them that it would be completely safe, completely fine, and every system will work well. In spite of that, they still expressed doubts, like I mentioned, in the capabilities of the system. And with each form of platooning, we again explicitly explained, saying that, yeah, you can take a break in this truck, for example, or sometimes you'll have to be transported between trucks and so on. So we had a slide, we had a small set of slides that we showed the drivers to make it pictorial and so on.
Okay, and maybe related to this, there's another question that asks about can we expect other benefits from truck platooning? So maybe in the realm of safety, or maybe more flexible driving hours. So maybe instead of making a job obsolete, it could maybe make it more attractive, for instance.
Potentially. Safety, I think, is a bit of a tricky one because in theory, yes, everything is automated in a platoon, so everything is supposed to be more safe. However, some studies say that drivers around a platoon, for example, change their behavior. They see these trucks driving in short headways, so they tend to automatically also start driving in short headways. So it definitely reduces collisions, but the broader effects of safety, I don't think have been studied into that much yet. And in terms of more flexible driving hours, I think definitely. But at least for where the driver is needed, I don't think it will be that much more flexible because of regulations, because drivers need breaks and so on. So especially a long distance trip, it would maybe make a difference of an hour on either side, but otherwise not so much. So these could definitely be seen as attractive, something that's attractive about the job. But what it takes away seems to be more important to the drivers, at least the ones we spoke to.
Yeah. Okay, well, thank you very much for that. We will go to the next presentation. Not before I mentioned to you that Joost van Tomme from ASEA put a interesting link in the chat box. I think this goes to the ASEA automated driving roadmap. So specifically for truck platooning. So I invite you to take a look at that, and you can find some more information on that. Meanwhile, Simeon has come online, and please go ahead, Simeon. We will take some questions at the end of your presentation.
Okay, thank you very much, Tom. So my name is Simeon Calvert. I'm an assistant professor at the Department of Transport and Planning at the TU Delft. And today I want to have a look at the concept of meaningful human control and how we can use that in practice for vehicle automation. Now, let me see how we continue with this. There we go. Now, some of these headlines might be headlines that you might have seen or something similar. So things like what self-driving cars can't recognize may be a matter of life and death, or stop saying driverless cars will help old people, or autonomous vehicles won't make roads completely safe. Driverless cars are stuck in a jam, or the one at the bottom is maybe the one that you most will know, deadly crash with self-driving Uber. Now, I'm not a pessimist, not by a long way. I actually count myself as an optimistic realist. I think as being a realist, some of these headlines do highlight some of the difficulties that we have with automated driving. Now, in the last 10 to 20 years, but actually leading up to that, the last 50 to maybe 80 years, there's been a lot of development with vehicle automation. And a lot of that has been especially focused on the technological challenges. And it still actually is to a large extent, especially with the OEMs, with the manufacturers. And at the same time, increasingly, we're understanding that we also have challenges in regard to maybe the more ethical or the behavioral aspects of automated driving. And this has been known for a while, but it's only maybe really started to get a lot of attention in the last 5 to 10 years. And especially in regard to vehicle design, maybe it's not something which is quite caught up with the technological advances yet. So this is something that I want to address in regard to the Meaningful Human Control project in this presentation. So what I'm going to do first is just give a quick recap on what Meaningful Human Control is, because I don't think everybody was at all of the previous college tour presentations. So I think it's And then I want to focus on why it's important to consider operationalization of this concept. So I'll touch upon some of the core components, and then I'll look at a qualitative example of where we can apply it to truck platooning. And then after that, a more quantitative operational example that really shows what we can actually do with the concept when it's applied in practice for specific cases. So to start with, meaningful human control is a concept that basically started from the defense sector. So you see that drone there. That drone is completely autonomous. It can fly all by itself, and it can decide when it's going to shoot its rocket. Now, obviously, you don't want something like that doing things that a human would not find acceptable, especially the human that sent that drone out. So we see a robot, basically, that has to adhere to some sort of human intentions or reasons, even though it's autonomous. So we've taken this concept and translated it to automated driving. Basically, an autonomous vehicle is a robot, but we don't want this robot, this autonomous vehicle, or automated vehicle, if it's a lower level, to perform tasks or do things that are not humanly acceptable. We want it to drive in a way that we desire it to drive with following our intentions. Part of the Meaningful Human Control project focused on more the ethical side of this, another part on the behavioral and psychological side, and the third part on the more traffic and engineering side. And my involvement was mainly on that last one, in trying to work out how we can take this concept and actually apply it in practice. So within Meaningful Human Control, we have two main conditions. And these main conditions are the tracking and tracing conditions. The tracking condition is basically that each automated driving system should track, so basically should follow the human reason of whoever is involved with that system. So a reason might be to perform their tasks safely. That could be one of the human intentions. Could be to perform certain routes or follow a certain route. So these are human reasons that the system must be able to track. At the same time, we have the tracing condition, which says that basically the automated driving system should always have some sort of human user that can be traced in the chain of control. So this means that if the vehicle performs a certain maneuver, then it should be able to trace back to where that maneuver was either programmed or was a driver who influenced it. So some sort of human actor. So these are the tracking and tracing conditions which are key to meaningful human control. Now, to say a little more on that, this is a slide that Julio showed in one of the previous lectures, and I'll touch upon it for a short time. On the left side, we see the more philosophical action. On the right-hand side, we see a more engineering view. So here we see what we call reasons in the center section. And these reasons are generally things that we as humans may desire a system to do. So there may be more distal intentions, and one of them could be to go home. And if we were talking about that in more engineering terms, that would be a strategic decision, so to go home. From a more operational perspective, something like steering is a task which would be operational, and those are more proximal intentions, but they're still intentions that a human being might have, and the system needs to be able to track, even if the system is the one in control, in operational control. So before we continue, I have a quick question. So again, using the polling options, how well do you think human ability and morals are currently considered in automated driving systems? And you could do this for any automated driving system you may be familiar with. It could be adaptive cruise control. It could be the Teslas that you see out on the roads. And for whatever system you think, but how well do you think the morals and the human ability are considered? I'll give you 5 more seconds to answer this. 3, 2, 1. Okay, so we see that the majority of you actually think that it's many of the moral and human ability parts are not actually properly considered in the systems, let alone all of them. So I think this is also falls the line of thought that we've found when we've looked at many systems, and we've found that a lot of the technical challenges are addressed, but when it comes to actually the human and the ethical parts, there's still some work to do. So this is also why there's some challenges, I think, and some of the challenges that also maybe the automotive industry needs to address. But some of the challenges really come down to, well, if you have a concept like meaningful human control, it's very abstract. So I hope all of you have managed to understand the 2 conditions I explained, but still it's a very abstract concept. It's not something that you can easily just stick in a piece of software or change under the hood of a vehicle. At the same time, it's also bound to many ethical and behavioral interactions, which are also not straightforward. And I think also it's collectively subjective to a certain extent. So if you consider norms and values, these are very subjective terms when you actually consider society as a whole. So trying to translate something like that into a more engineering concept is also difficult. But operationalization really allows us to do this in practice, and this is what I want to show in the rest of this presentation. So how have we approached this? Well, basically, firstly, we need to consider what are the core components that we're looking at. So we've done this, and I'm not going to show you this today, but we've done this for the vehicle, for the drivers, for the infrastructure, for the environment. I think it's a few other things. So for example, a component of the driver could be their cognitive ability to maintain attention, or it could be distraction. It could be their reaction time. For the vehicle, it could be things like the acceleration rate, or the pedals, or it could the sensors that are available. And from this, we've managed to develop also a simulation modeling framework, something, again, I'm not going to show you today. Today, I want to focus especially on the conceptual application to a specific case, and this is truck platooning, which fits quite nicely today. And then the fourth one is looking at the quantification of these types of operationalization. So how can we actually do some maths with it, for example, or simulations? So those last 2 I'll focus on in the rest of this presentation. So I don't need to introduce truck platooning, because I think Anirudh already did quite a good job at explaining what truck platooning was. But when we can consider truck platooning control, I think looking at the operational control of a platoon, and we have the front driver who is steering and is also controlling their pedals, but we also have the platooning system, which could be also considered as a CACC system. So that's a cooperative adaptive cruise control system. The human control is basically with the front driver in that situation. Now, when we look at the operational control of the following trucks, well, we have obviously the platooning system, which is there, and it depends on the type of system. But in many cases, it's certainly going to mean that the following truck has to monitor the system and maybe in some cases actually steer. But the human control of the whole platoon is still with the front driver, because the following drivers, their trucks are basically still following the front truck. So when we look at responsibility, on paper, we still see that the responsibility of a truck lies with an individual's own driver. This is a certain principle. Now, I know that this has been looked at, but still in practice and probably legally, this is still the case. So you see here that effective control is potentially confused when we look at actually who's in operational control against where is the actual control. So I want to show this also with a little example, which hopefully should make this much clearer. So the situation is, and we have a truck platoon that approaches a work zone. So something like the picture you see here. The truck platooning system does not detect the work zone and does not make a request to the driver. Now, this is actually not completely unrealistic, because this has happened with some automated systems that could not detect a work zone properly. And the front driver was either distracted or thought that the system could deal with this situation and reacted very late, but at the last moment did manage to steer away by performing an emergency steering maneuver without crashing into the work zone. But because the following trucks could not follow that leading truck because it was an emergency maneuver, and the trucks were not designed to perform this type of emergency maneuver when following because it might be unsafe, the trucks would then transfer control back to the drivers. But being such late in the process, the drivers only had a matter of seconds to react and couldn't, and the following trucks collided with the work zone. So what we see here is a certain problem that the following truck drivers could be held responsible because basically there's a certain demand that says that they must monitor their own trucks or monitor the system, and if need be, they have to react. And in this case, it's maybe not reasonable to ask them to react in time because of either the short amount of time that they have to react, or because distraction also might play a role. And you can imagine that if you have somebody who's monitoring a system for maybe a few hours in one go, that they will get distracted. They won't be as attentive as they were maybe when they started out. So just analyzing this using tracking and tracing. So the tracking, again, that is basically the system responds to the human reasons. Now, technically, the system has responded to the generic reasons of the main driver, that's the front driver, because the platoon is en route and it is compliant within the way it has been designed. You may argue with that, but actually that argument then would come to the tracing condition, and I'll explain why. Because the tracing condition is basically the ability to trace the chain of control back to a human actor. So we'll look at the human actors. The front driver, well, obviously he did not react in time because he thought maybe the system would be able to cope with this situation. So he didn't have a good understanding of the system, or he was distracted. In any case, there wasn't full meaningful human control there. The following drivers, that was also not met because basically there was either an unrealistic demand put on their role to monitor the system, which meant that they couldn't react in time. But also in regard to the designer of the automated driving system, again, there's not really meaningful human control there either, because the system is not designed to perform these types of really sharp turning emergency maneuvers. And for some reason, it did not detect the work zone either. So you can't really blame the designer in regard to the sharp maneuver. So to this extent, there is no human being who could then basically be held responsible or certainly be traced back in the chain of control. So we have a control gap here. So this is one of the difficulties with having automated systems in which the human is not an operation control, but still has to influence the system. In this case, we see that there's not enough influence of a human being in the system. So basically, we see a disalignment in control and responsibility here. There's a misbalance in the operational control versus what a human can actually effectively do. And we also see maybe behavioral capabilities of the drivers. It plays a role. So we have a misbalance in what a driver could actually be expected to do at certain points. And that also throws up some ethical issues. Can you nominally assign humans within such a situation to actually have these tasks when actually science has shown many, many times that the drivers will get distracted, and in other situations, true behavioral accountability is maybe not fair, even if we do have it as a legal accountability. So I want to move on now to our second example, and that's looking at how we can actually then start to quantify the meaningful human control concept and maybe use it more for design purposes. So the previous example was more on the type of evaluation purpose of using meaningful human control concept. So if we start with the meaningful human control theory, which basically was tracking and tracing, and we have system components. So I explained some of them already. If you do that on either vehicle level or driver levels, you can define lots of different components. And combining these allows us to come up with a taxonomy of control flows. So basically looking at how control is achieved from a meaningful human control perspective. So we're not necessarily talking about operational control, so that's hands-on driving, but who is meaningfully human from a human perspective in control. So that could also be the designer of a system. So I have two of these slides. I won't go into this in too much detail, but this just gives a bit of this taxonomy, which shows how we've tried to connect various parts of these components. So for example, the tracking condition, so that's basically the system should track human reasons, means that we have to have the human, so basically the agents. These could be either internal agents, so for example, our driver, or they could be external. So that could maybe be a traffic controller, or society is even a certain agent. And they can have their reasons. And as I showed, these could be values and norms, or they could be strategic, tactical, or operational. But from that, behavior occurs, human behavior. And that could also be driving behavior. And these you can also attribute to some of these actors. So we can close the loop like this. Now behind this, we also have some mathematics that I'm not going to show you, but that describes basically how these things interact. Now we can do the same for the tracing side, and I won't go through the whole of this, but just to give an example, the tracing side is looking at, is there a human agent in the chain of control? And part of this is also looking at the human ability. So, for example, ability is also subject to knowledge and capacity. So, for example, as somebody had training, it could be formal training like driving lessons, or it could be more informal training. What's their experience? For example, have they had regular, have they been driving more regularly? So obviously we know that once you get your driver's license, actually you learn more after you've got your driver's license, possibly than you learned before. So you learn from experience, so that's regular, but also some irregular types. So for example, if you've had an accident, you could learn a lot from an error. So we've done this also for other aspects within this tracing condition. But to keep it really simple, we have an example, and this example focuses just on two of these reasons. And before I explain what they are, first the case. So the case is basically a fully autonomous vehicle that's trying to overtake a cyclist. Now, we did this case together with the University of Glasgow, so this is a British road, so he is driving on the right side of the road. And this autonomous vehicle has a choice to pass the cyclist at a certain time, so when it thinks it's safe, and also a certain distance from the cyclist. And you can see that the cyclist is not driving in a straight line, as we know cyclists don't, but is wobbling a little bit. And we've done this looking and focusing on two specific reasons, just to keep things simple, because it's already complicated enough. So these two reasons were, the first one was duration. So a human reason could be, I want to get from A to B quite within a reasonable time, so not take too long. So that's the first one. The second one is safety. So obviously you want to get from A to B safely, but you can find actually that these two reasons can be in conflict. So if you try and get somewhere fast, it might be unsafe. And if you try and be safe, well, you might not even leave point A, or it might take quite a long time if you're looking for optimal safety. So there's a balance there. We've put this into some of the mathematics that was behind the taxonomy, and I'm not going to explain this control scheme, but I'm just showing to show you that there is a sort of control scheme, and this is a simplified representation of it. And we did this experiment 200 times in the computer. So there were 200 attempts of the vehicle to pass the cyclist. And what we found from this is that a number of times the vehicle had a bad experience. So on this top graph, we see every time there's a black spike here, the vehicle has experienced a bad overtaking experience, which could be that it got too close to the cyclist or maybe hit the cyclist. And we let this run for 200 attempts, and we see gradually that as the attempts go on, it's learned to avoid these bad experiences. And after about 85 attempts, there are no bad experiences anymore. And also this light blue line indicates how close the vehicle got to the cyclist. And actually we see that it increasingly chose a larger distance to pass the cyclist, which is good because then avoided unsafe situations. Now I should point out it couldn't get too far away from the cyclist because then it would also have a critical situation with oncoming traffic on the other side of the road. So there's also a boundary there. We can also see what this meant for the reasons that we put in. So that's the reason of safety and the reason of duration. It's maybe not quite as obvious here, but both of these lines here are increasing. So with each iteration, with each attempt to overtake, the reasons were met to a higher extent, so the human reasons. Therefore, meaningful human control was also met to a higher extent, which we've shown from this has a positive effect on, in this case, passing safely or not having a bad experience. And it also meant that the cyclist could be passed faster. So on this bottom graph, the black line shows how long the vehicle took to pass the cyclist. And with more attempts, it took, in general, a shorter time to pass the cyclist, which is a good thing because we wanted a fast pass, even though it had to be safe. And we can also look at what happens within a single attempt to pass the cyclist. So again, the red and the blue line are the reason for duration or fast and the reason for safety. And we see at a certain point they find an equilibrium. So that's basically that the vehicle has observed a gap that it finds acceptable to pass safely, and it has got to a certain point that it's started becoming maybe slightly impatient and wants to pass faster. And that equilibrium point then is the point which it decides to make that attempt to pass. So this is what we're optimizing. So from this, we can see that we can translate the concept of meaningful human control into something more tangible, something that we can actually do simulations with or do some calculations with. So it's not something which stays abstract and everybody nods and says, yeah, do you know what, guys, this is a great thing that we have to have, but nobody knows what to do with it. So we've actually managed to operationalize it in the sense that this is something then that starts to become a tool that can be used. And for this previous example, we've done this in a way that you can actually start to design your vehicles, for example, or design your systems, or maybe even design your infrastructure in a way that meets meaningful human control. So within this example, I only put 2 reasons, but obviously you can put in any number of reasons that you find important. And they could be societal reasons, or they could equate to maybe the drivers. And from the previous example with truck platooning, we showed also how we can evaluate more qualitatively such a system, so in regard to truck platooning that was, and see maybe how a system can be improved by using a use case to seek out where maybe things might go wrong or have gone wrong in the past. And we have a paper on this actually in which we've reviewed some of the accidents that have taken place in regard to automated driving. Now, being able to do this, both for design and evaluation, then also opens up the potential for us to influence policy in a very tangible way, rather than just saying we have this cool concept, but we don't really know how to use it. So before we start to conclude, I have a final question. Where do you see potential applications of meaningful human control in your own practice or your own subdomain that you're a part of? And you see things there. So what I want you to do is stick a comment in the chat box about where you can see potential applications of this. And we'll come back to that in a minute. So this is not the end of the story. So this is the end of my presentation. And even though we're also moving towards the end of the Meaningful Human Control project, we have come up and we've hopefully shown within the project that proper AV systems do require ethical and behavioral considerations. And Tom mentioned this at the start of this session. This has also been looked at within the European circuit. So also we want to pose a question, how does your AV system, so the system that maybe you're involved with, how does this consider these ethical or maybe behavioral questions? And are you willing to investigate options to maybe look at meaningful human control in your own system? So what I'm basically saying now is we have the building blocks and we're open to collaborating with either new partners or existing partners to see how we can start to apply these more and more in practice. So with that, I am done with the presentation and I'm willing to take questions. And I'm also curious to see what you've put in the chat box.
Yes, thank you, Simeon, for that interesting presentation. I don't see any in the chat box anything appearing regarding to your last question. However, there are a couple of questions to you, so maybe we can start with that. We have 5 more minutes left in the session. So there is a question on legislation may transfer responsibilities to the front driver from a liability or insurance point of view. Is this a problem or a part of the solution?
I would say it's a good question, and it's a question I probably could have expected. I would say it's a solution in regard to the legal side. It's not a solution in regard to the system side, because even if you nominally say that responsibility lies with the front driver, there are still situations in which it's maybe not ethically or behaviorally acceptable to still have that responsibility with the front driver. And actually, the case that I showed also demonstrated this, that the front driver did not understand properly what the truck platoon could actually do and reacted too late to the work zone. So in this case, the responsibility would lie with the front driver, but it may not be meaningfully humanly in control in regard to where actually the real problem lies. So you still have these accidents occurring, even if you can still assign legal responsibility. So this is where we see the gap between nominal control and maybe actual meaningful human control.
Okay, thank you. Another question is that for the passing the cyclist, it says in an AV setting, by times to pass the cyclist, do you mean that this is a completely unfamiliar situation?
Well, in the case of the cyclist, in the first instance, yes, the vehicle would be unfamiliar. The vehicle would know that it would have to take into consideration safety, so a certain safe distance, but it wouldn't necessarily know what a safe distance would be. And increasingly, the system has learned what is safe. And this was the original setup would have been in regard to a cyclist that would just drive in a straight line. But we intentionally put a cyclist in that was wobbling a little bit so that the system had to kind of recalibrate.
Okay, there's another, well, it's not really a question, but more a request. Someone says, I would like to see a translation from the driver license capability demands to functional requirements for AVs. Not sure if this is possible, because maybe I can weigh in on this as well. I think a lot of the capability demands that we have for humans that operate a vehicle are quite implicit, and humans are very good to deal with that and judge a context. If this has to be transferred through functional requirements towards software, it has to become very much more explicit. Maybe you can comment on that.
Yeah, I think it's a fair question or a fair point to make, but I think it's a discussion which is very broad and certainly one which is challenging. And I know that there are some organizations looking at this, but I do think at this point we're not quite there that we can have this full-on symbiotic relationship with the automated vehicle, from the point that we can actually have function requirements with the automated vehicle and have specific roles for the driver. So I think this is a process that we're still involved in.
Okay, well, thank you for that. We are in the final minute of this session, so and also we have answered all the questions from the chat box. So that means that I would like to ask, I would like to thank you both, Simeon, Anirudh. Thank you very much for your interesting presentations. Thank you to the audience for your undivided attention. And you can see all the materials, you can find them on the website. And please make sure that you come back in a couple of weeks for the final webinar. Thank you very much for your attention, and see you next time. Bye-bye.